And so also about after people give the talk, can I turn off my camera or do I?
Yes, you can. Okay, but if you'd like to now introduce the session, Lan.
Hello everyone. Thank you for joining us in the parallel section on compact objects binaries. My name is Lan Kinh Nguyen from the University of Notre Dame. Before we begin, I would like to tell you about our section. We can have 6 talks. Our first 3 speakers are Storm, Laura, and Jesus. After the first 3 talks, we can have a 15 minutes break, and the section will continue with the 3 other speakers. As you know, you are welcome to have a question. A question may be submitted via the chat at any time. If you wish to ask a question verbally, please raise a hand or include a comment with your questions on the chat. Questions from the live streams on YouTube are welcomed. All the questions will be answered at the end of the presentation. Each speaker will have a 15 minutes for a talk and follow with the 5 minutes Q&A section. I could remind the speaker at minute 12. Now we have our first speaker, Tom Walk, from the University of Washington in Seattle. He can tell us about the gravitational wave sources in our galactic background, prediction for binaries black hole, binary neutron star, and a neutron star binary detectable with LISA. Tom, please go ahead.
Great, thanks. Okay, let's see if I can share these. Now, also, I lost my bag through Aer Lingus, so I'm presenting from my tablet. So I think my video may disappear, I'm afraid. And you can hopefully see my slides in just a moment. We're a bit ahead of ourselves now. Sorry.
That looks good.
Great. Okay, so there's my title slide gone. There we go. So, thank you very much for having me. Very excited to be here, very excited to be speaking. So I just want to thank all of these various institutions. You can see all my various co-authors that you can see kind of orbiting me in their little circles. It was very much a group effort. So I'm excited to be kind of talking about these black holes, black hole neutron stars, and double neutron stars with Lisa. And my goal for this is to kind of answer 3 main questions for you. I want to tell you how many black hole and neutron star binaries I think Lisa is going to detect, what the properties of those detectable systems are going to be, and then I'm going to discuss the dependence of these results on kind of underlying binary physics assumptions. And I should point out there are lots of previous related studies that have done similar sorts of things, but we've kind of built upon these and done some new things as well. So let's get to it. First, I'm just going to start with a bit of an introduction, get us all motivated and just as excited as me about all of this stuff. So what we're focusing on here are stellar mass binaries in LISA. I'm sure you've all seen this plot 1,000 times if you've seen any sort of LISA presentation. And you will often be focusing on this area in this session. So these are the kind of galactic stellar mass binaries. We're going to detect them far before they merge. But what we're looking at is not just those double white dwarfs that everyone knows and loves. We're actually looking at the black hole and neutron star binaries too. And that's what I'm going to be focusing on today. And so I just want to briefly go over some kind of differences between space-based and ground-based detectors for people who might not be familiar. We're looking at a different frequency range. We're looking at lower frequencies. And so what this means is that we're going to detect the in-spiral phase rather than the merger. So these things are still going to be kind of orbiting around each other when we detect. And what this means is that we have a different detectable volume. So instead of seeing things out to like gigaparsecs in distance, we're actually only really going to be looking within the local group and mainly within the Milky Way. And this might sound like a disadvantage, but in many ways it's sort of an advantage because you know the environment of the sources of it better. And so that can be useful. And another thing I just want to highlight is the eccentricity. So whereas kind of the norm for a ground-based detector is that you'll have circularized systems, the kind of norm with space-based detectors, it's perfectly potential for it to have some form of eccentricity. And it can actually be quite high. And that can be useful for distinguishing different sources, which I'll talk about a bit later. And so why bother with these black hole and neutron star binaries? Why are we interested? Well, we can learn a bunch of different things. I mean, the obvious one is the kind of insights that we can get into the endpoints of massive stars. but we can also measure the Hubble constant. We can learn about the neutron star equation of state, R process enrichment, all sorts of interesting things. But we could also do a lot of those things with ground-based detectors. So why use LISA? What's the point for that? Well, the population tends to be quite complementary to ground-based detectors. We're not necessarily looking at those higher mass black holes. We're kind of focusing more on the lower mass, and there's lots of other differences as well. Eccentricity, as I mentioned, and that kind of gives us better insights into everything. And we've also kind of got opportunities for multi-messenger detections. So we've got LISA, and we will have LISA and the square kilometer array. And we could look at kind of pulsar and pulsar black hole binaries, and there's also opportunities for multi-band detections. So LISA could warn a ground-based detector that there's going to be some system that's going to merge in X number of years. And we can better constrain things, because LISA will measure the eccentricity well, and then the ground-based detector can measure the mass ratio well, for instance. And so that can be useful. So hopefully now you're super excited. You want to learn more. So let's talk about exactly what we've done and where we've got these results. So it's essentially a three-step process. Step one, we're gonna need some binaries. So in order to do this, we use the Rapid Population Synthesis Code, or Binary Population Synthesis Code, COMPASS. And these simulations are specifically done in Floor's paper. This is Floor Brook-Garden. And these simulations are cool because we do 53 different metallicities, which is many more than previously done, and we find this is important. We have 20 different physics variations, so varying underlying physics assumptions for binary physics and things like that. And overall, we've simulated over 2 billion massive binaries, so it's really quite a huge sample that we use. And so once we've got those binaries, well, then we need to put them into a Milky Way. So we then populate this a Milky Way using a couple of models kind of put together. So we've got Neige Frankel has kind of helped us with this, and we've used her thin disk model with a thick disk as well and a bulge as well. And these are calibrated to apogee data, and they're also metallicity dependent distributions. So the birth time and location of a system is dependent on its metallicity, which is more complex than a lot of the other work has focused on before. So now we've got them all in the Milky Way. What we need to do is then evolve their orbits until present day, calculate the signal to noise ratios, and then just apply some threshold and say which ones are detectable. And so we did this using a Python package called Legwork, which is something that me and Katie Breivik have made. And I'll talk a bit more about that later. And so then it's just repeat. So just kind of randomly simulate another Milky Way, evolve them forward, calculate the signal to noise ratios, get a statistical sample, and we've got some results. And so now I can kind of show you a bit about what we've seen. So first thing I think everyone likes to see is, what's the number? So we estimate that for our fiducial model, because we've got 20 different physics variations, this is just for our fiducial model, we'll get about 120 detections in a 4-year LISA mission. And they're distributed roughly like this. So the majority of binary black holes, you've got quite a lot of black hole neutron stars, and then just a smidgen of double neutron stars sprinkled with the rest. And in a 10-year mission, if we extend it, what we'll find is about 200 detections. And the scaling that you're seeing there is this usual, it scales with the square root of the observation time. So that's what that is coming from. But I think the numbers aren't necessarily the most insightful thing to look at. I think it's more interesting to look at how things are distributed. So a common way of doing this is looking at a sensitivity curve. And what we've got is this figure from the paper. But I'm not going to go through all of these panels because the bottom one's separated by type and it gets a bit complicated. So what I'm instead going to do is just kind of zoom in on the panel that just shows all of the different types together. And we're going to step through this bit by bit. So let's kind of get rid of some of that chaos and just build it up from the ground. So we've got on the x-axis frequency. So on the left, you've got low frequencies, right, you've got high frequencies where things are closer to merging. On the y-axis, you've got the amplitude spectral density. So that's just giving you can think of it as the strength of the signal or the strength of the noise. And this purple curve that you're seeing is the LISA sensitivity curve. So this is showing you how high the noise is for a different frequency. And so let's add some kind of grid lines to guide your eye. So what these grid lines show, the vertical ones, are showing you the in-spiral time for a circular system with the average chirp mass of the sample. So the average chirp mass is shown there. It's about 3.4 solar masses. And so you see on the left, things merge in about 1 billion years. On the right, they merge in like 100 years. So you can see they're accelerating across that plot. And the other grid lines I'm going to add are some diagonal ones, which show you some distances. So these are the distances at which a circular system with the average chirp mass would be detected. So the kind of higher up you are, the closer you are to the Earth. And so let's just put some sources on here. So these are from Thomas Kupfer's 2018 paper, the Lisa verification binaries. And basically the way you read this plot is the ratio of the height of the point to the height of the sensitivity curve gives you the signal to noise ratio. And so if we instead now plot all of the sources that I found in my paper, this is what we see. So you can see it's now a density distribution. It's not just points because there's so many of them. So otherwise it would just be oversaturated. And you can see that they're generally detected at lower frequencies than those verification binaries. And you can see a couple of different features. So let's go through them. You can see, first of all, you just got that gap. And the reason you've just got a gap between the sources and the sensitivity curve is we say for a source to be detectable, it needs to have a signal to noise ratio of 7. And so that's why you see that gap between them. You also see that most of the sources are concentrated in the galactic center. You can see the peak of the density distribution is pretty much lining up with that 8 kiloparsec line. And so you can see most sources are detected where most sources are formed. So that's sort of kind of as you would expect. And then the other thing is you might be worried. You see all of these sources kind of hanging out down to the bottom right, and they're past that 30 kiloparsecs. And that might worry you. You might think, oh no, they're out of the galaxy. Don't worry. If you remember, I said those lines only apply for circular systems. These are actually where the eccentric sources lie. It's quite nice. All of the eccentric sources tend to lie in that kind of bottom right-hand corner, just because the eccentricity means they're emitting at different harmonics and so different frequencies, and they kind of get shifted weirdly. But that's kind of nice. The eccentric sources are in that one location on the sensitivity curve. And then finally, you'll notice that the density distribution kind of drops off as you go to the right of the plot. There are fewer systems at higher frequencies. And the reason for this is what I first talked about with those grid lines. On the left, you take 1 billion years to merge, but on the right, it only takes 100 years. So you spend much more time on the left-hand side of the plot. So you're far more likely to detect things on the left. So this is kind of the shape of the distribution of sources on the sensitivity curve. And hopefully you now can understand all those points and tell your friends. So let's also look at some of the detectable properties of the system. So I'm not going to go through all of them. This is just, I'm showing you only 2 out of kind of a bunch in the paper, but I'm going to focus on the eccentricity here because I'd like to highlight a couple of things. So what you've got on the x-axis here is just eccentricity on a log scale. So things on the left, very circular, things on the right, very eccentric. And there's kind of 3 regions I want to highlight. I want to talk about the effectively circular region. Anything below 0.01, the eccentricity isn't really going to have much of effect on how long it takes to merge or how long or how strong the gravitational waves are. But then between 0.01 and 0.3, I'm calling it mildly eccentric. It's a bit stronger then. You see some effect, but it's detectable, but the effect isn't that strong. But the highly eccentric systems, you're then going to have the higher harmonics emit more strongly than the base harmonic, and also see them merge much more quickly. So those are the regions that I'm splitting them up into. And what we find is, this is again just for our fiducial model, but we find that only about 25% are effectively circular, whereas about 16% are highly eccentric. And this is quite different from what earlier people have done. What we saw previously is that lots of people kind of assume that everything's circular, and we do not find that that is true. So that's eccentricity. And then another one I want to show you is the mass distribution. So this is the component mass distribution for our fiducial model. And so what we've got here are both the primary and secondary from all of the systems, and it's weighted by detection rate. So the black holes are more important than the double neutron stars, for instance, in this. And so this is kind of the shape that you see. You've got the mass, just the distribution. And I should note here, we're using the Fryer 2015 delayed remnant mass prescription. This is going to be important in a moment. And I also want to highlight this does extend up to 18 solar masses, but just kind of goes down smoothly. And I want to focus on this lower region, because right here, we've got the supposed lower mass gap, this possible observed mass gap, where we have a dearth of black holes and neutron stars. And what we find is that for all of those systems, those 120 systems in a 4-year mission, we find about 55% have one of its components, so either the primary or secondary, in this lower mass gap. I do want to highlight this is dependent on the physics assumptions. So if we use a different remnant mass prescription, if we use the rapid one, it looks like this blue curve instead. And so what you see is then you don't get anything in the lower mass gap, and that's because that prescription is designed, not to produce anything in the lower mass gap. So of course we're not seeing them. But I just want to highlight that is going to be dependent on your physics assumptions. But we find that it's still a sizable fraction. And then the last plot that I want to show you is our detection rate across different physics variations. So we've got these 20 different physics variations. We've got things that focus on mass transfer, common envelopes, physics, supernova, and stellar winds. And I'm not going to go through all 20 in detail because I'm not sure anyone would enjoy that. But what I want to highlight here is just how different the detection rate is across different assumptions. So what I'm showing you on the y-axis, on the left, you've got the kind of detections in a 4-year mission. On the right, you've got the detections in a 10-year mission. And the kind of gray highlighted region is showing you the fiducial model with its 1 and 2 sigma errors. And you can see that across different assumptions, you're changing by kind of orders of magnitude. And so I want to highlight to everyone, it's super important when we make predictions for LISA that we really make it clear what physics assumptions we're using in any sort of population synthesis. Because if you don't, it's going to be very difficult to compare between different papers. Even nicer, use lots of different physics variations, and then you can see how things change. And so this is just binary black holes. If I kind of zoom out and look at all 3, then black hole neutron stars you can see vary a bunch, like 2 orders of magnitude. And then double neutron stars don't vary very much, but that's sort of because the models that we chose vary lots of black hole physics rather than neutron star physics. But big takeaway here is that the detection rate is going to vary significantly over those model variations. It's going to go between 30 and 370 over a 4-year mission. So it's very important that we are considering physics assumptions. And so last thing I just kind of want to leave you with before I go on is perhaps you want to make your own predictions. Perhaps you're interested in working with LISA. You've got some sources that you're interested in. And maybe you don't want to do all of the work yourself because it's a bit of a hassle. Well, what I would offer you is, why don't you let us do the legwork for you? This is me making awful puns, but this is a Python package that Katie Breivik and I have made, and it will evolve sources, calculate strains, signal-to-noise ratios, sensitivity curves, and it also visualizes all the results. So if you remember that plot from earlier on, that one is made entirely with legwork. And you can find all the documentation online. You can just install it just by pip install legwork. But if you'd rather have it told to you rather than read about it, you can come to my other talk later today. So if you go over to the parallel session B, instead, I'm the last one later today. So I'll be excited to talk more about that as well. So thank you for listening. Here are my takeaways. So you've got my fiducial model with the various detection rates, things about eccentricity, and the lower mass gap. Got you some links for the papers because I think I'll share these slides later. And what I'll just leave up is some possible areas for discussion of things I couldn't quite get to during the talk. So yeah, thank you.
Thank you, Tom, for very interesting talks. And now is Q&A session. Everyone, please raise your hand if you have a question. Yeah, Tom, I have a very small question in the slide. You show the low mass gap. I saw a peak in the low mass gap. What is mean as the peak?
What did you say? Like a dip?
In the low mass gap.
This one?
Right. Yeah. So I saw the peak there.
Oh, the peak at like 7 or 8 solar masses in the rapid case. Yeah, this is it's basically entirely down to the way that the kind of rapid remnant mass prescription is described. So kind of you get a lot of systems with different masses all get placed onto the same remnant mass, and so you kind of get this pile up at a certain mass. And it's because a lot of the sources that were going to be in the mass gap kind of get shifted higher up. So that's why you end up with that peak.
Okay, thank you. And
sorry, Lan. Alexander, could you go first?
yeah, please go ahead and introduce yourself and ask a question. Alexandra, please.
Yes, and Alexander, I now allowed you to unmute yourself as well. Sorry.
Perfect, thank you. Great talk, as always, Tom. I'm curious about that 5th point you have there, as always, with the multi-messenger detections. Do you think we're actually going to be able to see any of these?
I think it's going to be difficult. So I think pulsars are really going to be the focus for this, I think, because most of them are going to take, let's see if I've got it here somewhere. Most of them are going to take, like, if this bottom right panel here, like 1 million years to merge from after LISA. So we're really going to be focusing on the things that are immediately multi-messenger. I did a little bit in in the appendix of the paper about possibly using the square kilometer array with LISA. And I did some kind of back of the envelope things with the kind of sky location errors, which I've got here as well, like the angular resolution, and seeing like what you would need and how many pulsars would expect to be there and how difficult it will be. My rough summary is, it's going to be hard. I think it's going to be like order of 0 to 5.
I mean,
yeah. I mean that's you know it's 0 is in the range, but it's not definitely 0.
Exactly. All right. Thank you very much.
Thanks for the question.
Leave, you're next.
Okay. Yeah. I can read the question. Can you the question from the can you please yeah I think Tom, can you read the question on the chat and answer the question?
I'm not sure Tom can, so I'll read it for you,
Okay.
Lan. It's from Neha Singh. I apologize if that's incorrect. They say, great talk. Can you please elaborate on the galactic potential you assume to evolve the binaries and if one can customize in legwork?
Okay. So when you say galactic potential, does this mean, so I assumed that the kind of kicks and evolution within the galaxy was kind of negligible. The orbital evolution that I'm talking about is just within the binary. So the galactic potential doesn't really come into it as much. I assume that they're going to stay in, roughly the same location, because there's so many of them that the angle doesn't necessarily matter. They're just kind of going around in circles, I'm assuming. And the orbital evolution is just kind of taking gravitational wave emission and saying how long will it take until it merge. And so there isn't any sort of galactic potential stuff in legwork, but you could possibly do something with that with Gala, the package by Adrian Price Whelan, which I have used for a similar sort of thing before. Hope that answers the question. Feel free to clarify.
Yes, the next one, Laura, please unmute yourself and ask question.
Thanks, Tom. It was a really nice talk. I was wondering, what is the source of that kind of bimodality in the distribution of eccentricities for double black hole binaries?
Got you. Yes.
Yeah.
So it's basically, it comes from the way the direction goes. So you can either get highly eccentric systems if you get lucky with the kicks and the directions. So if you kind of at this in-between eccentricity, then you're going to end up disrupting a lot of your systems, kind of whatever angle you go at, except for very, very few. But the highest eccentricities, you can get it if you just angle them so they're like pointing right at each other and it just kind of kicks you inwards, then you kind of get an extremely tight system that's extremely eccentric, and you can get lucky with those. And so that's where kind of all those would come from. They're kind of like the lucky kicks. Whereas the kind of more marginal ones are where the fallback affects things and you get a weaker kick and just kind of like this more mildly eccentric rather than highly eccentric. Yeah.
Okay, interesting. Thank you.
Thanks.
Okay, thank you, Laura. And then the last question came from Katie. Kate, please unmute and ask question. Yeah.
Thanks, Tom. This is great. I was kind of following up on Laura's question. Do you look for correlations in chirp mass and eccentricity at all?
I think I've made that plot very long ago, but not recently.
Okay, yeah, it might just be interesting to see what those are in terms of disentangling between like dynamical formation channels.
Yes, I remember we nearly made this plot at one point because you used it in that different paper. Yes, definitely interesting. I will look at that as well.
Thanks.
Okay, thank you, Tom, and everyone for very nice talk and very nice discussion. Our second talk is about detecting the environment of stellar origin of black hole binaries by Laura from Albert Einstein Institute. Laura, please go ahead.
Okay. Thank you, Lan. Yeah, so I'm Laura Sberna. I'm a postdoc at the Max Planck Institute for Gravitational Physics in Potsdam. And I'm going to tell you about work done, as you can see, with a large number of people from the LISA community over the course of a few papers. So the topic of this talk will be trying to understand what LISA could learn about the environment of stellar mass black hole binaries. And to answer this question, I first need to explain to you, if you're not too familiar with this topic, how can we measure, something about the environment from a gravitational wave signal. Well, the reason why we can detect environmental effects is that these can, leave an imprint on the gravitational wave signal by changing the way, the binaries in spiral to merger. So if you have in mind a chirping source, you can look at the phase of the gravitational wave signal as a function of frequency. And we know that the Einstein's equation in vacuum predict a certain frequency dependence of the phase. In particular, you can expand the phase in a post-Newtonian expansion in powers of the velocity, assuming the velocity is small. And we know that environmental effects can predict new different ways in which the phase can depend on the frequency. So you would have new terms in this expansion. In particular, you can have terms that have a lower, frequency dependence compared to the vacuum ones. So you can distinguish them from vacuum prediction. And this is why LISA is a particularly interesting mission to look for these environmental effects, because it's sensitive, as Tom said, to lower gravitational wave frequencies. If you have in mind the quasi-monochromatic sources like the ones Tom was looking at, in a similar way, environmental effects can affect the way the frequency evolves in time. And so you're going to have modifications to these f dot, f double dot terms. So what I just described is a direct way in which the environment can affect a gravitational wave signal. But of course, we can also have indirect imprints of the environment onto a population of gravitational wave sources. And this is a bit what LIGO and Virgo are trying to exploit by looking at correlation among the population of sources, to try and infer not just the environment, but the evolution history of these binaries. So now that I've told you a little bit how the environment leaves an imprint on the gravitational wave signal, let me tell you why we're interested in learning about the environment in the first place. Well, the truth is that the environment can be both a blessing and a curse. In terms of blessings, if we think about stellar mass binaries, as we just heard, one of the main questions about these sources is how did they form? And the technical and environmental effect can be, a telltale sign of a formation in a dense environment, such as an active galactic nucleus, an AGN, rather than the binary having formed in isolation. And again, LIGO and Virgo are currently trying to address this question, studying the population of sources. But a direct detection of an environmental effect in a single source could really distinguish these two, even when population properties are, less identifiable. And of course, if these stellar mass binaries are located in an AGN, we can hope by detecting an environmental effect to learn about the AGN itself. So we might try to learn about what the density of the gas in the disk is, what the viscosity is, what disk models best describe this disk, and how black hole binaries accrete when they're in such a dense environment. And of course, we could also try to learn about the properties of the supermassive black hole at the center of the AGN, And this would be yet another way in which LISA sources could measure supermassive black hole properties or massive black hole properties, besides massive black hole binaries and extreme mass ratio spirals. But as I mentioned earlier, environmental effects can also be a curse. And this is the case when you're interested in using LISA to test general relativity. This is because environmental effects can mimic in their frequency evolution modifications of gravity. One clear example is a slow varying gravitational coupling G, which has a frequency dependence in the phase that is just the same as the effect of accretion, constant accretion onto the binary. Of course, we might hope to distinguish modifications of gravity from environmental effects in a number of ways, using, by perhaps detecting an environmental counterpart, identifying the host environment in the electromagnetic spectrum, or perhaps looking at the population properties. So going back to our stellar mass binaries in AGN disks, these are, an ideal source to look for environmental effects because the disk in the AGN is providing you with matter effects, so with accretion onto the binary or dynamical friction. And the presence of the supermassive black hole at the center is giving you third body effects. So for example, the Doppler modulation caused by the orbit around the supermassive black hole. And these two are somewhat related to each other because one of the ways of having a binary migrate so close to a supermassive black hole is by having migration torques and migration traps that then keep the binary at that special location where these third body effects are important. So for the rest of the talk, and to give you a concrete example, I'm going to use the event GW190521 as a model source. This was a source detected by LIGO and Virgo. I'm sure you heard about this. It was a very, interesting signal because the two binary masses were very large, one of them clearly in the upper mass gap. And already the masses, therefore, were indicating that perhaps this source was not formed in isolation. But on top of that, there was also the detection of an optical flare by the Zwicky Transient Facility, which had a proposed association with GW190521. Of course, this is just a model for our source, but our results don't depend very strongly on the precise type of, on the precise masses of the system, for example. So finally, I'm coming to the results of our studies, and I'm going to tell you how LISA could detect those environmental effects that I mentioned a couple slides earlier. So what we found on the matter effects side is that LISA could detect the effect of accretion and dynamical friction. So these are two effects that come in at low gravitational wave frequencies. They can be treated perturbatively, and we can write their phase contribution in a very simple way with these two powers of the frequency. And we can parameterize them, with some assumptions by the constant accretion rate onto the binary, onto each of the components, and with the disk, the local disk density rho. And what we found is that LISA alone could detect the presence of accretion and dynamical friction, although for somewhat large values of these parameters, a bit above the realistic values. So for example, super Eddington accretion. But if we consider a multi-band detection where LISA is working in collaboration with a ground-based detector, then realistic values of these parameters become, come within reach. For example, we could infer the value of sub-Eddington accretion rates. But as I mentioned, the the fact that these binaries are in an accretion disk also puts them close to a supermassive black hole at its center. And it turns out that the orbital motion around the supermassive black hole can actually be the largest environmental effect. So to explain this, I'm showing you the standard, vacuum frequency evolution as a function of time of our gravitational wave source. And what you can see is that the frequency grows over time in a very simple monotonic way. So what happens when I put this source in motion around the supermassive black hole? Well, if this motion has, a period that is similar to the observation time of the LISA mission, so 1 or 2 years, then the Doppler modulation of this orbit is very significant, and it actually causes the frequency evolution to become non-monotonic. You can see that the frequency goes up and down here around the vacuum prediction. And this is simply given by treating the signal in the time domain and adding this time-dependent delay, based on the simple circular evolution around the supermassive black hole. The reason why, first of all, you can see by eye that this modification of the signal is going to be very important and clearly detectable. But this also makes our parameters estimation a bit more tricky. And this was the main, realization and contribution of our study. We realized that you cannot simply add this modification in the frequency domain. You need to be careful by starting in the time domain, dividing your signal into monotonic phases. In these phases, you can apply the stationary phase approximation to go to the frequency domain. And finally, you can do your parameter estimation in the frequency domain, as you usually will do. I want to mention that besides the Doppler effect, you can also have a detectable Shapiro time delay, so caused by the gravitational influence of the supermassive black hole on your gravitational wave signal as it exits this potential well. The Shapiro delay is in general subdominant to the Doppler effect, except as you can see on this slide, when you have very small inclinations between the outer orbit around the supermassive black hole and the line of sight. But actually in this case, lensing would also be important. So in the next slide, I'm going to go back to the case which you saw before, I guess here, where the inclination is more generic, is larger, and so Shapiro is subdominant to Doppler, but still detectable. Oh, the binary needs to go around. So finally, when you do have a detectable Doppler and Shapiro delay, and the two are really important together to be able to break degeneracies, then LISA could, in these stellar mass binaries around an AGN, measure the central black hole mass 2% level. This is a very nice result because such a precision on a supermassive black hole mass is only achievable in very close supermassive black holes, such as Sagittarius A star or M87, or a few other black holes where there's some special emission going on close to the black hole. There was a positive result coming from an environmental effect. Of course, as I mentioned before, there is also a bit of a dark side, because we find that if you try to model that same signal, try to detect or analyze that same signal with a vacuum waveform, so if you were not aware that these environmental effects were possible at all, then you might lose SNR, as you can see in the panel on the left. And at the same time, when you have not lost the SNR completely, so you can still detect the source, you might still have sizable biases in the parameters of your source, for example, the chirp mass or the time of coalescence. And this can be mildly important for astrophysical purposes. Really, the chirp mass has not deviated that much. But the presence of this bias is an indication that, for example, tests of GR would be very off for these sources.
Laura, do you have a few more minutes left? Okay, thank you.
Yeah, I'm wrapping up. So yeah, just to summarize, I showed you with some, very detailed full parameter estimation studies that stellar mass black hole binaries in AGN, if detected by LISA, could help us measure some interesting environmental and astrophysical properties of these binaries, such as their accretion rate, or the local disk density, or the supermassive black hole mass and the distance from this supermassive black hole. As I mentioned, lensing in certain systems can also be important and detectable, so we're working on that next. And I want to mention that environmental effects can also be important in other LISA sources, such as extreme mass ratio in spirals. And we recently put on the archive a work on this topic. So thank you.
Thank you, Laura. I don't see any question in the chat at end, but I saw the raise hand. Alexander, please go ahead. You can unmute yourself.
Sorry, I was actually just clapping. This is really cool work. Do you know how these mass measurements that you think you could get of the central black holes compare to the sort of things that we can do from the standard electromagnetic observations?
Yes, I said, I think that a precision like this one is only possible with electromagnetic observations for a handful of sources, where I think you have these mega masers close to the supermassive black hole, and you can measure their, maybe their Doppler shifts as well. Mm-hmm. I don't quite remember, but it's only a few of them.
Very cool. Thanks.
Okay, thank you. And I don't have any question or raise hand in the chat. We also run out of time, and let's thank to the Laura. And and we go to the next speaker. Is Jesus, and he can talk about the stellar origin of black hole binaries, which LISA forecast on background detectable and the number of observable events in the LIGO third catalog of gravitational wave detection. So, Jesus, are you ready?
I am, thanks.
Yeah, please.
So I should be allowed to share my screen, right?
Right, yes.
Can you hear me fine?
I can hear you clear and loud.
Fantastic. Thank you. So I'm a little bit underslept, so I hope I will manage to do it in a allotted amount of time. So this is work done in collaboration with other people from the Cosmology Working Group, in particular with Stas Babak, Chiara Caprini, Dani Figueroa, Nikos Karnesis, Paolo Marcoccia, Giovanna Nardini, Mauro Pieroni, Angelo Ricciardone, and Alberto Cesana. And what we set ourselves to do, we started actually when the 03 run of LPK wasn't out yet, and then enlarged the work to include 03. We wanted to take the population inference on stellar origin binary black holes from LIGO Virgo Cagra and see what does it mean for LISA, both in terms of the background and of observable events, or possible observable events. So all of you have seen this very nice picture that represents all the events, not only stellar origin binary black holes that LIGO and Virgo detected. In particular, we are interested here in the clear blue ones, which are around 70. And as probably all of you know, the emerging event is preceded by a long spiraling phase, during which the frequency is practically constant, and the frequency and amplitude increase until we have the merging events and some ring down of the binary, of the not binary, or the X binary, let's say. Also, as all of you know, LIGO, Virgo, and later Cagra will be able, or have been able, to see the merging of these events and the breakdown and the closest of this phase to the merging, whereas LISA will see the inspiraling of these events. LISA will integrate a lot of data over time and take the spectrum, so it will see these inspirals as peaks, maybe a little extended, depending on the frequency evolution. And we will be able to figure out some of these peaks, but most of them will actually form a confusion noise. So we have these two elements that we will study in these couple of papers that will come out hopefully very soon. So with these 70 events, or around 70 events that I mentioned, LIGO and Virgo, or the LIGO-Virgo-Cagra collaboration, perform some inference on the parameters of these individual events, and then with this inference, they doing hierarchical modeling, they did some inference on the population, or a number of population models from which these events could have been drawn, which definitely was probably one of the hardest things that actually they did. And it's actually a very nice paper, the GWT3 paper, to read. So what does it mean in our case? So if we forget about the individual events and we only look at the population parameters, population inference, we can try to compute with this posterior the prediction for the background in LISA, and we can compare this with LISA detection capability for a background of this kind, and we can try to compute a probability distribution for the number of events that LISA would see. So first of all, let's take a look at the population model. This is the one used, the classical population model that contains a merger rate, or we shouldn't call it in the case of LISA merger rate, so a rate of binary black hole events in a particular amount of time and comoving volume, then a term that accounts for, you can see my mouse, right?
I
take it.
see it.
Yeah. Okay, thank you. So this term that accounts for the change in volume with time of the comoving volume, the change in physical volume. Then the number of time during which events are generated, and then a probability distribution for the rest of the parameters of the binary. So masses, spins, alignment, these kind of things. And the shape of R and P and the hyperparameters is theta of each of them determine the population model. So for the measure rates, we do what is usual in the field, which is following the star formation rate. Obviously, this is not true. At least there must be some delay between the formation of stars and the formation of stellar origin black holes, but to the level of precision that we will probably be managing with LISA. And at least for a few decades, this is probably enough. A crucial assumption here is that if we want to use the inference by LIGO, LIGO was looking at merging events, and these events are relatively late in time. So indeed, LIGO and Virgo only, sorry, it says LKV instead of LVK here. It's only produced inference on this term on the top, so this power law, which is this blue band that you can see here. And we need to extend this towards the past. So a crucial assumption in our paper is how to do this. The way we do this is we choose to fix the other two parameters, which is an optimistic in terms of uncertainty approach, but it doesn't matter too much in the kind of comparison that we are doing. So we can discuss this at the end if you want. This is the usual merger rate when one extends it to late times, except for this factor, kappa over R here. These are subtleties that we found that we can also discuss later if you want. And when we are looking at individual events, as we said, we really care about just the really late times. But when we look at the background, we have to integrate the whole thing. So we need to extend at least to z equals 5. In particular, of all the models that LIGO, Virgo, Cagra tested, we are interested in the one that was called parallel plus peak. A parallel plus peak refers actually to the distribution of masses of the heaviest event in the binary, heaviest mass in the binary, but also the inference that we are managing on the rest of the parameters depend on what you choose for this, right? So we can also call parallel plus peak like the full model. And it's called parallel plus peak because probably as many of you know much better than me, on top of the typical inverse power law for modeling a population of events for which there is not much knowledge of the mass. So it only assumes that there is a lot of non-massive events and a few massive ones. It takes into account that there is a range of masses of stars that tend to collapse to a reduced range of masses because of the way they shed mass. And it introduces this pileup as a Gaussian, and it turns the full probability distribution into a mixture, which is called a mixture probability between these two probabilities, like the inverse power law and the Gaussian. The amount of Gaussian there is actually, so the value of the mixture parameter for the Gaussian is like 0.04, so it's not a huge deal. So what happens with the background? So if we have chosen a population model and we have chosen parameters or values for the hyperparameters, or if we want the parameters of this population model, there are a number of ways we could compute the background. We could take this population model with its parameters and do an analytic integration, as we see, or we can realize a synthetic population and then either do a Monte Carlo sum of the analytical computation or run a full simulation. As for the analytical calculation, this is known since a long time ago. As simple as, and if we are talking about the spiraling phase, of course, because this would be slightly different, so the formulas would be different, in particular for the amount of energy radiated by a single binary. So this would be different in a merging event, but in an spiraling event, it was computed already in 2001 by Finney. Well, probably this one is not by Finney, but the interrealities is the amount of energy radiated by a single spiraling event. So if we integrate this over a number density, and then integrate the number density over whatever density was defined for, so redshifts, volume, etc., we can get the value of the background that this population generates. And in particular, if we inject a particular population model, we can get the value of the background for this population model. In any case, the frequency goes out of the integral, and it is a universal fact that for a population of spiraling events, we have a slope of f to the 2/3 when talking about the background in omega h square units. What different population models give us, or different parameters for the same population models, are basically just the value of the amplitude. So all this complexity actually, in terms of the background, it translates into a single number. So we could have taken this integral over a population density, a number density, and turn it into a sum of a realized population. This will give us an approximately equal result, but gives us the advantage of having an estimate, having a handle of how much variation we may expect given a population model coming from the different draws that we can take from this population model. So a sort of cosmic variance, what in CMB is called cosmic variance. So we just did this test for the range of parameters that LIGO, Virgo, and Carollo, and we found it to be very small. And as for the simulation, we don't expect to run a simulations all the time, because we are talking about hundreds of millions of events in the universe. So definitely we cannot run simulations. So we want any way to run a few simulations to see that we can trust our analytical computation or not. And for this, we use this method developed by 3 of our collaborators and 2 other people that start by simulating a full population, averaging the spectrum, turning and treating it as a background, and then computing the signal to noise with respect to this background of all the events, subtracting the loudest ones, and repeating these steps until the background stabilizes. And this way one gets both the subtracted events and the background. So it's a very clever approach. And when we have compared this to the analytical calculation in the regimes that we are interested in, we found it to be concordant, as long as, or only taking into account that we can only subtract loud events if we don't want to subtract also background. So we are subtracting events, or considering subtractable events that have signal to noise of 8, which is actually typical in this situation. And if you stay, let's say, with darkest blue line, we see that this follows it perfectly, except for this, which is not a physical effect. So it's a limitation in our synthesis of the population. So, but we have tested that when we extend this, this disappears. We can also talk about more carefully if you want. So we saw that we can trust the analytical calculation. So this is what we did. And what we did was starting finally results from the population inference from the gravitational wave transient catalog 3, taking all the samples, because the data that part of the data that has been made public is a posterior sample from this power Laplace peak model, and compute the background in all these cases. And this way, we get a distribution for the background in the frequencies that interest Lisa. And this distribution is given here by the blue line. We want to characterize this distribution, so we draw some percentiles, typically 595, 2575, and then the median 50. And what we did was to inject the value of the background of these percentiles in our Lisa stochastic rotational wave background code. And what we found is that Lisa is approximately 20 times more sensitive than the prediction for the background of LIGO Virgo Kagra. So any background within the ones that are expected by LVK is very easily detectable by Lisa. And because of this precision, and this is very, very preliminary work, not part of what we are publishing, but like our next step is like, well, if this is so, we expect to be able to put stronger constraints on the population parameters. So on the one hand, this would be true. On the other hand, if you remember, I told you that in terms of the background, not of individual events, all the complexity of the model only reduces to one number, to the amplitude. So on the one hand, a lot of precision on measuring just a single number containing all the population information. So for a test event, if we just basically select the events in the LIGO Virgo posterior sample that are compatible with the background, with the median background, for example, we can see that we would narrow the range of allowed parameters in some particular direction. So the one that we would constrain the best here is, should say, kappas and are not. So the behavior of the measure rates at late times, and also a little bit the slope of the power law of the strongest mass. But anyway, this needs a more careful analysis. I'm just showing you this as a kind of showing off the potential of Lisa when measuring the background more precisely. And then I promised to talk about individual events, so only 2 more slides. So how did we get a prediction for individual events? So we have this nice fast simulator that I talked about that would give us the background and individual events, but we also said that full simulations of the full population that have hundreds of millions of events are not possible. So since we contrast the analytical computation, what we did was for each point in LIGO's posterior, or for a subset of them, if we wanted, but we did the full thing. We generated a sub-catalog that only contains loud events, and this loud being defined by an approximate signal to noise. And then we injected these events on top of the analytical computation of the background for the same parameters of the population for which we generated this subset of loud events. And we used this code to see how many of them would be subtracted. So doing this many, many, many times, we arrived to the following probability distributions for events. And in particular, we found the rather disappointing fact that Lisa will not see many in spiral. So if we are going to trust that LIGO's inference on the posterior of the power Laplace peak model are extend towards Lisa, and this is the right model, we will not see many resolvable in spirals in Lisa. So we'll see, let's say, around 10. But there will be loads. So on the one hand, let's say these 10 will merge relatively soon. We expect them to merge in the next decade. So we expect to be able to have follow-ups, seeing them merge in future experiments. So next rounds of LIGO, Virgo and Kagra, ET, etc. And there is a lot of potential for archival search. So if we reduce our signal to noise threshold, we see that the number of events that are in the data with a significant but non-detectable signal to noise is higher, so grows quite quickly. And if we have something which is not really detectable by LISA, but it's in the data, and then a later event is able to detect this signal with the prior coming from the later detection, we can go back to the data and actually find this with this thinner prior, and then increase the amount of constraining power that we had when combining with LISA. And that's it, basically. I'm not sure, I wasn't looking at the clock, so hopefully I didn't go too much over time. I leave you here with the conclusions. Thanks to the organizers for letting me present our work. So thanks from the whole team. And if you have questions, I'm here. And if you want to follow up by email, my email is easy to Google, I guess. Thank you.
Thank you, Jesus. And it's time for question. I saw several hands up. At first, it's Kathy. Yeah.
Hi, thanks for this great talk. I'm curious about whether y'all have thought about including eccentricity in this somehow. And the reason for that is I wonder if it is a way to sort of reconcile predictions coming from population synthesis that show that we think that the sources are eccentric regardless of their rates. And maybe an eccentric population is like passing to the LIGO band more quickly, and maybe we see pileups in LISA. I'm kind of trying to reconcile why we get different rates when you work from the LIGO rates alone versus population synthesis, and hoping that maybe eccentricity is the way to do that. So I'm curious if you've thought about eccentricity.
No, we haven't, but definitely we'll look into that. Is there any, so if there is any reference, if you can pass it to me via the chat, I will definitely read it and definitely share it with my colleagues.
Yeah, definitely. So I can at least pass references for eccentricities coming from predictions from sources so that there's something to work off. But yeah, okay. Thanks.
Yeah, thank you. No, sounds very interesting, because at the end of the day, it's a huge extrapolation what we are doing. So it relies on, it strongly relies on assumptions about, well, in this case, no eccentricity at all. So definitely,
right.
Cool. The matching can change a lot. Thank you.
Yeah, thank you, Kathy. And the next question came from Chris. Yeah, please. Thanks. Chris, please unmute yourself. Yeah. I cannot hear you.
Sorry, it's Neelemans. If you are speaking, we can see that you're unmuted, but we can't hear you. So
can you hear me now?
Oh, we can hear you now.
Yes.
Sorry, there's something funny with the audio. Sorry. So I had a question about the detectability of the background. Does it depend on the assumptions for the high redshift population density model? Based on the shape, if you understand what I mean. So I didn't fully understand that, but I guess you are looking for a very specific frequency slope, isn't it?
Well, the frequency slope does not depend on the particular shape of the merger rate or the binary rate in this case. But what it does depend on this assumption of extension towards high redshift. What does depend is the shape of the blue line here. So and the shape of the blue line, so the width of this distribution will basically tell us very quickly. So the error band, so the uncertainty prediction, the width of the uncertainty prediction around this blue line here. So if we, for example, allowed for more uncertainty, or if there was a sudden decay here towards early times, for example, then LIGO's prediction would be displaced towards smaller values of the background, and then LISA detection capabilities for this the allowed range would be slightly worse because the value of the background expected is worse. But we are not very deep at all into LISA's potential to measure the amplitude of a power law with this low. So indeed, this plot has a logarithmic axis here, but if we plot it linearly, you would see that this thing is so narrow that basically the LISA error bar is the same in all cases. So if we go not super surprisingly low, so if we had a huge decay here, for example, here, probably LISA would still be able to, most likely LISA would still be able to see it perfectly.
Okay, thank you. Can I ask another question, or do we have to wrap up?
Yes, I think you can have another question. Yeah.
If I'm not mistaken, but I may be mistaken. I thought that previously we believed that we would not be able to detect this background. Is that correct?
I haven't been in LISA long enough to know what
I think there's some studies from
believed.
like 20 years ago or so, which I think concluded that you probably would not detect such a background. But anyway.
I haven't been in LISA this long, but in this sense, I think I can quite confidently say that we will be able. So in particular, for example, for this computation of these error bars, we have used 4 years, and we have actually used the 3 channels using TT to constrain the high frequency noise better. So we have done a sophisticated enough analysis. So I don't know. I mean, I guess something really surprisingly would have to happen. Like actually there is nothing beyond 0.5. So what LIGO sees is all there is, or something like that.
Okay, thanks.
Okay, thanks, Chris. And there is one question in the chat from Elena. I can read it out loud. Hi, Jesus. Nice talk. If you would analyze together the detectable background and the several resolved individual events, would you expect to get stronger constraint on the hyperparameter of the populations? Can you answer this for Elena? Yes, thank you.
So, I mean, the answer is obviously yes, no, but how much is the issue? The thing is that LISA alone wouldn't have a lot of constraining power on a model for stellar origin binary black holes, because again, if we are talking about measuring the background, we have a lot of precision, but we only have one number. So we would have a one-dimensional degeneracy if we only measure the background on a long posterior. So for example, we can see this narrow band here because what we are doing is just having a LIGO break this degeneracy here, and this is the direction of the degeneracy with LISA. But then when we added individual events, the thing is that there aren't that many. So ideally, yes, but there aren't that many. So there are only like 10 or so. So
yeah, so the reasoning is that these 10 events are very are special in order to be detected. They are not your average event, I guess.
Definitely.
So therefore, if you observe them, how many you observe and their characteristics should give much more information than your average event.
Absolutely. But still 10 events on a model that has, how many was it, 16 parameters is not a lot. So we are probably more likely, what we will more likely be doing is combining LVK individual events with LISA background and LISA resolvable, I think. But
thank you.
I don't know. You're probably more of an expert than me in this particular thing.
Okay, so I think we should thank Jesus. Thank you very much for the talk and for the very colorful discussion. And we will stop our first section here, and you can be back in the next one you can start at 3:13 p.m. in the Eastern time. So it's in about
10 minutes. Let's
10
10
minutes
minutes.
from now.
10 minutes.
10 minutes from now. Okay.
20 past the hour. Let's call it.
Okay. Yeah, thank you. And then see you there.
Thank you.
Thank you. Did you stop recording?
No, the recording will continue,
Okay.
both the recording and the stream.
Okay. Hi, Kati. Okay.
Shall we get started?
Can we start? Hi, everyone. Welcome back. And please go with our first speaker in this session is Thomas from Texas University. Thomas, please introduce yourself and your talk. Thank you. Can you unmute yourself?
No, now it works. I just got an error message like popping up. I can't unmute myself. It's like, okay.
I was keeping everyone in suspense.
Yeah, no, it makes sense. Sorry.
No, that was my bad. Sorry.
Sorry. Okay, let me share my screen first. Okay. Let's see. Side. Okay. Thank you everybody for coming, for listening to us. It's really a great meeting. I really have enjoyed everything so far. And so for the next kind of 15 minutes, I just want to give a brief rundown on galactic binaries and what we do on the EM side and how can that aid what Lisa will see in the future. And so I really just call this talk kind of Lisa meets Gaia. And so let me start with my favorite plot. I always show this just for the sake of, because I like it so much, the frequency strain plot. And you see that the dominant sources are kind of the bread and butter for Lisa. That will be galactic binaries, right? This is these purple dots here. We all have seen that. But I want to actually emphasize one point, and that's different, very different from what LIGO is seeing and so on. Lots of these sources, actually almost all of them, won't be tripping within Lisa lifetime. So you won't see any kind of change in the frequency, which means then that there's this degeneracy between the trip mass and the distance, right? So that's one of the things we have to think about when we think about these galactic binaries. Okay, so that's something to keep in mind. So when we talk about these Lisa binaries, especially regarding the distance, in 2018, when Gaia released their second data release, actually when parallaxes were released, this was the first time we actually received or got distances for a really large number of sources. And so that's something where we, for the first time, actually try to calculate characteristic strains. And that's a plot which is from our 2018 paper, where at that point, were what we call these verification systems, or sources basically which are SNR 5 or higher above for Lisa, and using these distances from Gaia. So let me say a few things about these 2018 sources. At that point, I don't think there has been really a systematic study to find these sources in a large scope. And so most of these sources you see here were purely serendipitous discoveries, right? Just falling out of a survey. Like HM Kangri is the 5-minute binary source system, which was actually detected first as an X-ray source. And then only follow-up observations showed this is actually a compact system. And so at that point, there's a strong overabundance in what we call AMCVN systems, which are creating white dwarfs. Theory not necessarily predicts that, right? We would expect much more double white dwarfs, which are shown here in red. At that point, the number of known sources were much more biased towards the AMCVNs, which is really due to the fact of how they were discovered. So that was what 2018 was. Well, let me now show you, or go slowly towards what we now know. And first, we have done much more work on trying to find them more systematically, right? There has been now several surveys, and I just want to give a brief overview of one of them because I was part of that, which was a survey with the Zwicky Transit facility, where we really tried to find these sources in a much more systematic way, and where we focused on specific parts of the galaxy, especially the galactic plane, and observed this part of the sky repeatedly with a very high cadence, and then really looked for short period variability. So kind of what we did was we went to a field, which is shown here in these squares. We observed this field repeatedly for over 2 or 3 hours. And then we looked for changes, periodic changes on this, and within these 2 or 3 hours. And everything which changes within 2 and 3 hours is potentially a very compact systems detectable for LISA. Everything which is not changing on this time frame is probably something else. So that was a survey specifically to find these sources, and that actually started in 2018. It's actually was ongoing for a few years, and I think it's still ongoing. And by now, this plot is actually a bit old already. This is stuff I published in this paper, but by now actually the entire galactic plane is filled, and we have a lot of stars. And it's really now a needle in a haystack search to find the short period systems out of these few 100 million individual sources. And that's a whole different topic which I will not go into. But over the time, we actually have found a few more sources. And just to give you 2 examples here, one of them is actually a new type of systems which we have not seen before, where you have a helium star and SDB star with a white dwarf in a very compact system where the helium star has started mass transfer onto the white dwarf. And another thing is on the right, you see this is actually a 24-minute double white dwarf published by Kevin Birch. And you see these little dips down here. These are actually eclipses. So this is a double white dwarf with a period of 24 minutes, and we see this from the eclipses. And you also see here why these high cadence data is so important, because these eclipse durations are like 1 minute or even less, and you really have to kind of stay in the field to exactly get this 1 minute eclipse time. But that has not been the only survey. There has been lots of work over the last kind of 4 years and even before, where people have tried to find these. And I just want to give a few examples here, outlining here. I think the other big one is what we call the extremely low mass white dwarf survey. And I want to make a kind of a shout out to my postdoc in my group, Alexander Kozakovsky, who is actually doing this work in the Southern Hemisphere. And they are also looking for these double white dwarfs, but they're looking particularly for extremely low mass white dwarfs, because they have to be formed in binary. And then TESS, SDSS5 had already contributed one source. And so over the last 4 years, there has been much more work on finding these sources much more systematically. And before I show you now the new updated strain plot and some inferences from that, let me show you quickly, briefly, how we actually get to these distances. Because keep in mind, when Gaia releases the data, it's parallaxes. Parallaxes is not a distance, okay? So parallaxes is a measurement, and well, naively you could say, well, it's just 1 over the parallax gives you the distance. That's only true if you have a really precise parallax. If the parallax is known to much better than 10%, then you can do that. But what we have done is actually try to be a bit more sophisticated. What we have done is we actually tried to use Bayes theorem, so kind of a prior knowledge on the volume density and the scale height, and then basically use that to infer the distance. And so what we did is we estimated the population of the sources. So are they particularly thin disk, thick disk, or halo? And based on that, we used the prior on the scale height, which we know pretty well now from Gaia, 400 parsec for the thin disk and about 800 parsec for the thick disk, applied that prior, and then used that to get the distance. It will not have a strong effect on sources which have a very high precision on the distance, but it has an effect on the sources which have a low precision on the distance. And so doing that, that's how the way we actually just derived our distances. And then the change, in particular from Gaia DR2 to EDR3, is actually quite significant. The parallaxes have improved by something like 20 to 30%, as you can see here, especially on the faint side, where the dark sources, so the fainter sources are. You really see this is the 1-on-1, and then it's 10% better, 20%, and 30% better. And you see that, especially on the faint side, 30% better parallaxes leads to much better precision on the distance, and then in turn leads to much better precision on the trip mass. And so that's just to keep in mind. So this is where we were 2018. I explained you now a few surveys we have done, other people have done, basically the way we derive the distance, and that's where we stand as of today. So these are the published sources as of today, and we're really building up sources now. So while we took decades to build that diagram, we have now within 4 years more than double the number of systems. I also want to say these discoveries are now much more systematic. So people specifically look for that kind of stuff, and you already see that the fill symbols are eclipsing sources. Right? And so eclipsing sources are easier to find in the photometric variabilities. And that's why we see an overabundance of eclipsing sources now compared to what we probably would predict. And that also means that, yes, we find more systems. Yes, we are more systematic, but the current population is still very biased. So that's something always to keep in mind. We're getting better, but we are still very biased. And I think we are not quite there yet to do, especially from the photometric sources, population predictions from the observational side. But we're getting much better and we're finding much more sources. But to show you how biased we actually still are, well, if you look at the sky distribution, most sources are located in the Northern Hemisphere. That's just because surveys are mostly in the Northern Hemisphere. You see that this is kind of the equator, and then everything up to the north is the Northern Hemisphere, to the south, the Southern Hemisphere. And so here in the Northern Hemisphere, it's mostly then SDSS and CTF and all these surveys who find the sources, and that's why they're all located there. In the Southern Hemisphere, it's still quite empty. We have a few of the AMCVNs from historic surveys or older surveys, and then a few smaller things which are actually now coming out of the ELM survey. And so there's a lot of work being done also now starting in the Southern Hemisphere, and then also in the future BlackGem, Bear Rubin Observatory, DR4 will provide photometry across the sky, will certainly help in the south, and over the time will probably do a much better job building up a sample across the entire sky to find these systems. So that's kind of where we are with the sky location. And so now to put another point on why we are so biased is this is now an HR diagram where we can now put these sources, because we have the distance, on an HR diagram. And you see this is kind of the main sequence, right? This very dark region here. Then this is the white dwarf sequence, and all these sources are above. And that's easy to explain from an observational point of view, because the bright sources are the ones we see. The bright sources are the ones which are easier to detect. It's just that simple. We have the helium stars SDB up here, and then we have the AMCVNs, the accreting AMCVNs here, and then we have the white dwarfs here, but none of them actually lies on the white dwarf track. And I would probably guess that most of the LISA predictions, LISA sources, will probably be on the white dwarf track, but that's not what we see, and that's purely observational bias because these sources are brighter, so they're easy to detect. But the good news is we're building up a sample. I think we are now close to 30 with an SNR of 5, and then we have really high SNR sources above 100, close to 10 now, right? So we are getting really there to find these high SNR sources. And so there's a GitLab, which actually Valeria started, and we're trying to keep this up to date as possible, where we list these, what we call verification systems, these sources which are SNR 5 and up, roughly. So we have this there. So let me know if you're interested. So I have a few more minutes, 4 minutes, something like that. And I want to spend a bit more time kind of just introducing something. When we see this plot, when we have this SNR 5 source, well, it's nice that we see that. And I learned yesterday, actually, they are, just because we know the frequency, already helpful for the global fit. But what can we really learn in the end? What can LISA add to that? Or perhaps add something which we don't get from EM, right? So there's these kind of ideas of how can they aid each other. And I think that's something really we're thinking about over the next years, also where EM might want to focus on over the next few years to make sure we are really ready for when LISA produces data. And that's something also the astrophysics working group, and Kais Nellermans is leading that work, trying to figure that out and do this kind of work. So and from now, I just want to show a few examples of work I have done with Tyson Littenberg on particularly the AMCVN systems. The AMCVN systems just are very close to my heart. I did my PhD on them. I really like them. And so, but the issue is that a lot of them show mostly accretion disk signatures in the electromagnetic bands. So it's very hard for us to learn much more from the electromagnetic bands because they are very much dominated by the accretion disk. But what if LISA does observe them? And let me say, this is kind of the golden sample. This is when I saw this is really awesome. AMCVN itself has an expected SNR of more than 100 after 4 years. It has a 1% level parallax precision on the parallax, so really precise. This is kind of really the gold standard. And if you put that in and say, what can LISA give us? It's really mind-blowing because we get a 1% level precision on the terminus, and we can a 10-degree precision on the inclination. That's something we not even close we can from EM. So that's really, really cool. And that's something I really look forward. So for those sources, I would argue just try to find them and wait and maybe work somewhat on getting the primary mass then to solve the chirp mass, but overall, LISA will give it all to you. If you look to little bit lower SNR sources, 1908 is an example, which is also an accreting AMCVN system. SNR is roughly like a few tenths after 48 years. Parallax is still precise, but not as precise. And here, the inclination is not as the inclination will probably still remain uncertain with LISA, right? So this is a prediction from Tyson Bayes as well. It's probably uncertain. And so these are different assumptions on the trip mass because we were thinking about, can we actually distinguish donor masses in these systems? And if you assume different trip masses, well, if you have a higher trip mass, of course you have a higher SNR, you get a better precision, but still it's not great. But there are evolutionary models which are either these systems move in or move out, and so they give different trip masses. And to a certain degree, you can distinguish different trip masses. So I think there's not a lot of, it's not completely hopeless, but it will be less precise. But here I would argue, well, try maybe to get a better idea of the inclination from the ground or a better idea on the trip mass, and then vice versa, you will help LISA, right? If you know the inclination to really precise values, well, that actually then nails down the trip mass pretty well, right? So here I would say we should probably try to do a bit more work to get either the trip mass or the inclination better from the electromagnetic observations. And so as the last point, as the last slide, I just want to give kind of a shout out and an advertisement to a work done of one of my former students, Anton Amelbert, who actually finished Texas Tech as an undergrad, and he's now starting a graduate program at SMU with Krista Smith. So he's going to the more massive black holes. And he has done work on the ultra-complex X-ray binaries, which is kind of the equivalent, but with a neutron star black hole accretor. And there's the same issue. We know them, we know where they are, we know the period for some of them, we know the distance to many of them because they are often in globular clusters, but we don't really know the masses or without assumptions. And so he has done work on trying to predict what LISA will actually do for us. And I encourage you to watch his pre-recorded talk to learn more about that. And with that, thank you, and I'm happy to take any questions.
Thank you, Thomas. And now it's time for question. Please raise your hand. Yes.
I can't find the button to raise my hand, but I do have a question. You mentioned something about the eclipsing systems on your plot, and I was just, this isn't technical, just the lines through, is that to define them as that they are eclipsing, or is that the error bar? I was just slightly confused.
Sorry, I probably should have done what, yeah. So the line through is the error bar, the predicted error bar based on the distance, based on the mass uncertainties. And then the filled circle is like, filled means that it's eclipsing. So we have a large overabundance of eclipsing sources, which is purely due to the detection method. So filled symbols mean eclipsing.
Okay. I perhaps missed that because I was busy with other things. Thank you.
Yeah.
Okay, thank you. And Kathy, please unmute yourself.
This is lovely. I'm so excited to see many more sources. Can you talk a little bit about the other detection strategies? Are all of the not filled double white dwarfs from like radial velocities? Is there any astrometry, and are people looking for them in Gaia DR3 now?
So exactly. Let me actually go maybe back to that slide. So the extremely low mass white dwarf survey, what they do is very different. They actually, extremely low mass white dwarfs have a very specific color. So they do a color selection plus a parallax selection, and then they do radial velocities. So that's mostly radial velocities. And so there you are also sensitive to the non-eclipsing sources. And so that's a different detection method. And that's also mostly the non-eclipsing sources are often, they're actually from the ELM survey.
Got it.
Right here. And then on the astrometry, well, I don't think they would necessarily show up in the astrometry because they're too compact. So Gaia wouldn't see them as astrometric binaries. I think that.
Yeah, I guess even if they're close enough, they're probably so close that we would have already seen them.
The other hope is, and I actually have not seen anything, but I hope somebody works on that, is the X-rays. Rosita should should see all the HM concretes in the galaxy. So the X-rays is another way, I think, which is promising with Rosita as this big survey now running, or kind of paused now, but they have 2 years of data and there should be plenty to look for these direct impact accretors on the short period side. So I think these are the main methods, I would say.
Cool.
Yeah.
Thanks.
Thank you, Kathy. And Elena, you are next. Please unmute yourself.
Hi, Thomas. Thank you for your talk. I was wondering, I think you didn't say that, but in your study of very high signal-to-noise ratio CVs, are you also looking at deriving the properties of the angular momentum transfer, looking at F dot?
Yeah, so that's something, that's a good point, because that's something we should be able to. So the hope is if we can measure the P dot from over the next 10 years, which I think is not completely out of place, which should be basically outwards moving, so not going in, but going out. And then we get the chirp mass with a very high precision. We know exactly the difference, and we know exactly what basically the astrophysical P dot should be. And then going from that, we can say something about the angular momentum transfer. I don't think F double dot is something, at least not for AMCVN itself. I think HM Cangri, there we have hope, because it's so compact. There we have hope. But for AMCVN, I might be wrong. I'm not a gravitational wave physicist, but I would think the hope is using P dot from EM versus the chirp mass, and that gives us the astrophysical.
Yeah, correct. It's exciting.
Yeah, this is super exciting when I saw this.
Next question is Tyson. Yeah, please unmute yourself and ask question.
Yeah, I'm more just piling on the last question. So
yeah.
I think we made these plots,
yes.
Your purple and green plots, where it's going the other way, where if you end up with this really nice chirp mass constraint, that becomes a constraint on how much of the P dot is coming from gravitational waves. And so even if the LISA or follow-on measurements are consistent with no P dot, it at least gives you a P dot budget of how much is coming from gravitational waves, and then therefore how much must be coming from astrophysics.
Right. Yeah.
And then your discussion about inferring the distance from the parallax is more complicated than just 1 over parallax. I think I was talking to you when I learned that parallax parsec is 1 arcsecond of parallax.
Exactly. That's
you
right.
learned everything. But I would find, because I'm an idiot, as I just explained, I would find it really instructive to see the inferred distance as a function of 1 over parallax, so you can see where those things start to diverge, just for my own sort of intuition building.
That's an easy plot to make. I haven't from doing this, I think it's about when 10%. But yeah, this is an easy plot to make. This is a good point. Yeah, because the reality is, once the parallax becomes really too uncertain, so if kind of the uncertainty is at the level of the parallax, well, then you're kind of getting the distance based on your prior. So you're really then kind of dominated entirely by the prior, and that's right. I mean, you can only do so much to infer the correct prior. So there's always this issue. If you are too uncertain, then well, it's in the end what you assume. That's what you get, kind of. So, but most of these sources are not that bad.
Okay, I think we have no more question, and that's thanks Thomas. And we go into the next speaker. Is Valadias from the University of Birmingham, and she can talk about the last magnetic clouds from the new perspectives from LISA. Thank you.
So let me set up everything. Okay. Okay, so with LISA, we will enter in the era of non-transient gravitational wave astronomy by observing the stellar mass compact object binaries that we were talking about until now. And as Tom highlighted in the first talk, this will merge on a time scales between 1,000 and million years. And so they are not going to be evolving within LISA. So although we are often, think of LISA as LIGO, I can argue that LISA will actually sees the sky through these binaries in the same way as Gaia will see. But of course, unlike Gaia, we won't have any dust extinction that makes a life of electromagnetic observers difficult. And in my talk, I would like to draw your attention on this, on one of the brightest spots on the sky, which I'm sure you recognize to be the Large Magellanic Cloud. And recently, Gaia has shown us that the LMC is a very important player in our Milky Way ecosystem, and that all accurate dynamical studies of our galaxy cannot be done without including the LMC's effect. So we are sort of living in the LMC renaissance thanks to Gaia. So from the LISA perspective, this galaxy is also interesting because it is the most massive of the Milky Way satellites. It is nearby and it is actively forming stars. And as such, it will likely host a large number of detections. And we can study those gravitational wave LISA sources in a completely different environment to our Milky Way. So this is how I believe the LISA sky will look like. And in red and yellow here, you see the density per square degree of the famous double white dwarf binaries that we expect to be the most abundant amongst the other double compact objects accessible to LISA. And on this map, you also see some stars and dots. And this represent known Milky Way satellites. So in a paper led by Eleanor Rober here in Birmingham, we studied LISA sensitivity to a fiducial source in each of these known satellite galaxies. And we did this study based on the, rigorous Bayesian detection and parameter estimation techniques. So here the stars are those satellites in which our fiducial source has been detected, and the shades of blue for those stars are telling you about the uncertainty on the sky localization for our fiducial source. So the question I would like to address next is how likely our fiducial source is likely to be in the Milky Way satellites, and there will be enough of these sources for the satellites to stand out against the galactic double white dwarf foreground. And we can answer this question using binary population synthesis model. So here I'm using the one from Sylvia Tonen that is constructed based on a code called SIBA. And here you're looking at the orbital period chirp mass parameter space. And in color, I'm also showing you the time it takes for the binary to evolve from the zero age main sequence to the double white dwarf stage. So of course, as you may expect, the more massive binaries evolve faster. And as we go lower down with the mass, then the double white dwarf formation time scales become longer and longer to the point to be comparable with the age of the galaxy. One tiny detail I wanted to mention. So this specific model is based on is fine-tuned and based on the observed double white dwarfs. So it's also reproduces well the observed space density that we measure from spectroscopic samples, and it also matches well the mass ratio distribution that of these binaries that is shown to peak at around unity. So now we take this population and we place it at the position of the satellite, and we inject our binaries at the rate that is dictated by star formation history. So here I'm using some examples. And let me, without going much into detail show you the results. So in this plot, we are looking at the number of detections in color as a function of the satellite stellar mass and the distance from us. And we repeat this study for different star formation histories, IMF, metallicities, and so on. So this is just one illustration, one simulation. And it tells us basically, if we look at this dashed thick line that is showing us the one detection contour, that satellites with the total stellar mass higher than 1 million solar masses can host LISA detectable double white dwarf. And if the satellite is located within a couple of 100 kiloparsec, these double white dwarfs can actually be detected by LISA. So I'm overplotting here a few famous satellites, but you can see that LMC, so the Large Magellanic Cloud, is our primary target. So it is expected to yield the most LISA detections. So with the former master student at Leiden Observatory, Michael Kame, we follow up on this idea. And Michael thought about a few models, few realistic models for the LMC, in which we, look at the star formation, we look at the spatial distribution, and we also vary the mass. And just by, at the end, by comparing the outcome of our simulation, we also want to assess how these ingredients, influence the detectability of these binaries with LISA. So our first model is the observation-driven one. And we call it like this because we're using a spatially resolved star formation history constructed by Harris and Zaritsky. And this is based on 20 million stars observed with the Magellanic Cloud photometric survey. So with such a large number of stars, you can actually dissect the LMC as was done here, and for in these tiny pixels. And for each of those, you can, fit stellar models, derive stellar ages, and build the star formation history. So in this model, we inject our binaries in this 2D pixels. According to the star formation history of the pixel, and the number of injected binaries per pixel is given by the integral of the star formation rate, that is that give us the total mass of stars in that pixel. So here on the right, you see our version of the LMC based on this study. In our second model, that is the simulation driven, we wanted to explore more the spatial distribution of the LMC and its peculiar features that are that I'm mentioning here on the slide. So the bridge between the Magellanic Clouds, then the arms extending towards the SMC and towards us, and we wanted to see whether these are visible with LISA. So this is so here we base our study on an antibody hydrodynamical simulation of Scott Lucchini that was specifically designed to reproduce these LMC features. And here we inject our double white dwarf population into the simulation particles according to the particle mass and the age of the stars within it. And again, on the right, you see our version of the LMC based on this model. And the third model is actually the combination of the best features of these two. So we took the observed LMC star formation history, and we combined it with the spatial distribution from this hydrodynamical simulation. So first, let me show you the double white dwarf formation rate as a function of time for the first two models. So the observation-based one is in blue, and you see that the formation of double white dwarfs is pretty shallow until 6-7 gigayear, and then we have a big jump and another jump of star formation that is believed to be triggered by the interaction with the SMC. While this is the gray line is the simulation-driven model, in which you see that the most of the binaries are formed within the first few gigayears, and there is very little star formation since. So our combined model by construction is then in terms of the formation history follows more closely model one that you see here, but there are some differences due to the different mass distribution. So let me show you the result in terms of the number of double white dwarfs as a function of the LMC total stellar mass. So on the top, we are looking at double white dwarfs emitting in the LISA band, and you see that the number scales linearly with the stellar mass of the LMC, and the three models predict roughly similar numbers all around 20 million binaries. But when we look at the LISA detectable binaries here on the bottom, you see that the model 1 and 3, so based on the observed star formation history, yield from a couple to several times more LISA detectable binaries than the one based on the simulation. And the reason is within the star formation history. So more recent star formation yields more LISA detectable binaries. And what we have learned from this plot, that while the total stellar mass of the LMC sets the total number of binaries emitting at the millihertz frequencies, the star formation history sets the quality in terms of detectability with LISA for these binaries. So very quickly, I want to show you the breakdown of detectable binaries in some categories. So this is for the set mass of the 2.7 billion solar masses. We have the range in total between a few hundred to several hundred double white dwarfs, of which from 50 to 60% are detached, and the remaining 50-40% may be in the interacting phase. And importantly, I want to highlight this last category that selects binaries with total stellar mass higher than the Chandrasekhar limit. So this will be exploding in the future as supernova type 1As. And this is very special category because, we haven't discovered not even one supernova type 1A progenitor in our galaxy. So LISA will be a crucial instrument for finding this. And we show that it will able to do that not only in the Milky Way, but also in the LMC. Again, here I'm showing you instead the distribution of the binary orbital period and the chirp masses. And I would like to highlight these vertical lines that show you the means of the respective distributions. And again, the blue and the yellow, so the models based on the observed star formation history sort of overlap, and the gray line differs a little bit. So these blue and yellow lines fall at larger orbital periods and higher chirp masses. And that's again related to the star formation history, because with the more recent star formation history, we have more massive binaries that typically also sits at larger orbital periods. So this can be a signature of the LMC star formation, past star formation history. And finally, I would like to mention that we will also learn about the LMC's total mass if we reverse engineer our models, and starting from the observed number of detections, we can look at our library of models that predicts the number of detections per solar mass, while we also vary the age, the distance, star formation history, and so on. And we can, infer in a Bayesian way the mass that was necessary to generate the observed number of detections by LISA. So here I'm showing you an example in which we of the posteriors on total stellar mass and the distance, in which we used for the inference a star formation history that is close to the observed one. So for these two models, we were able to correctly recover the total stellar mass with the more or less 20–40% precision. So since I'm running out of time, I'll just quickly skip to the summary, and basically let me tell you that we are now living in the times in which LMC is an active topic of research. However, all studies so far relied on electromagnetic observations, while LISA will provide us a new promising avenue for synergetic and independent studies of population of stellar remnant binaries. Now, this is formed in a different environment to our galaxy, and we will be able to do this with the multiple instruments that as I'm showing you here in a multi-messenger fashion. And from the LISA detection, we will also be able to learn about the LMC's mass content and star formation. And this constraint will be based on completely different selection effects, and thus they will be important to include for joint constraints with electromagnetic observations. And I'll stop here.
Thank you, Valeria, for the talk. And and I saw we have several hands raised here. At first, it's Antonia. Please unmute yourself. No, and
they might have been hands of applause. It was a very good talk. Maybe you could just comment. I don't have figures and values in front of me, but just how unfeasible or feasible is it to see any of these systems optically? And maybe, or perhaps Thomas could comment on that. But I'm just wondering if, given that we know roughly how far away the Large Magellanic Cloud is, maybe we can, it helps curtail its distance.
Yeah, so it's 50 kiloparsec away, so that's quite a lot for the dim stars like white dwarfs. However, if they are accreting, as I'm sort of showing here with the stars, we can see the X-ray emission produced by accretion, and so you can see them, for instance, with the X-ray telescopes. So that's is very promising multi-messenger way of combining gravitational waves and electromagnetic waves for the LMC.
Okay, and next one, Thomas.
Yeah, sorry, you might have said it. My internet is acting up a bit, so I might have missed it since you said it. But I was wondering exactly about the Athena detection. So how, I saw you had this nice big blob of signals, but for a given source, for especially the interacting source, how uncertain or how certain is how big will be the error circles roughly within the LMC, and will they be completely just a big blob and undistinguishable, or do you think you can pick out individual sources, especially if Athena gives you then a frequency, maybe you can identify individual sources?
Yeah, so I have a slide on the error bars that I had to skip, but basically the sky localization will be of a sub-degree square.
Yeah, that's good.
And Yeah, so actually that's smaller than the LMC itself. So we will be able to, say that those binaries are there. And in addition, LMC also sits in a quiet, not populated part of the sky. So that also helps to, associate them. I don't remember Athena's field of view, but I hope, it is the LISA errors may not be so bad for the synergies.
Okay, cool. That's really cool.
Okay. Thank you, Thomas. And the next question came from Alexander.
Hi, Valeria. Great talk. I was really cool to see the mass measurement. So that second model that you had, the different star formation history, you might have mentioned this, but can you explain why that results in a lower number of detectable sources? My naive thought would be that if you have more systems forming earlier, more systems should be at higher frequencies, so we should be better at detecting them.
Yeah, so I don't think I have a good plot for this in here, but basically, when with this with the recent star formation, you add binaries at all orbital periods, and you add also binaries close or directly in the LISA band, and this brings also the more massive. Maybe this plot. This also brings more massive binaries that in the old population, they would have already evolved. So this is why, for instance, the chirp mass distribution is slightly different when we have the, let's say, younger population and the older population. So you bring into binaries that are more detectable, and the star, like adding binaries via star formation, is more efficient in terms of LISA detections versus putting them all at the same time and waiting for them to evolve via gravitational wave radiation, because in this way you lose these massive binaries because they just merge very quickly.
That makes a ton of sense. Thank you.
Okay, and I think that it's the last question for Valeria. And let's thank Valeria again. And we will move on to the last speaker. Katis, are you ready? Yes. So yeah, the last speaker for our today is Katis. She can talk about the applying the metallicity dependent binary fraction to double white rock formation and how is the implication for LISA. And Katis, please go ahead.
Okay, so I should be sharing my front page of my screen and I can see my presenter notes. Great. Okay. So thanks to all the speakers in this session so far. It's been absolutely lovely and fantastic to learn about all of this new exciting science. Today, I'm going to be presenting the results of some work that was led by Sarah Thiel, who was a student that worked with me while I was at CETA. And she is not giving this talk today because she is presently figuring out a move from the University of British Columbia, where she did her undergrad, to Princeton for grad school. So she said she couldn't be here, but sends her regards. So in this project, we tried to take into account some new understanding of zero-age main sequence populations, namely metallicity-dependent initial binary conditions, combined that with a very precise set of metallicity-dependent positions and ages from the Latte suite, specifically the M12I Galaxy from the Latte suite of the Fire simulations, and then some binary evolution models with Cosmic. So throughout this talk, I'll walk you through each of those things to then show what we have found in terms of what LISA will see based on including a metallicity-dependent binary fraction on the zero-age main sequence. So first, let's talk about what observations we found. So it's becoming more and more stable at this point. There's really a host of results coming out from different surveys namely apogee, has played a huge role in this, that the close binary fraction of solar type stars is very strongly anti-correlated with metallicity. And what that means is that at lower metallicities, you are much more likely to form a close binary than you are at higher metallicities. Because sun-like stars, and specifically close binaries containing sun-like stars, are the progenitors of double white dwarfs that Lisa will observe, we thought that this was quite a very exciting opportunity to see what some observations that are actually like real empirical defined, there isn't uncertainties. Let's see how those propagate into our models for what Lisa will predict, which are indeed quite uncertain. So this result, what it actually means for the initial binary parameters is that a metallicity dependent closed binary fraction effectively just alters the initial orbital period distribution of the zero age main sequence progenitors of double white dwarfs. So what I'm showing here on the left is the actual, this is called the orbital period frequency. So the frequency of companions in closed binaries as a function of the orbital period. This is fitted exactly from this curve. And the way to understand this is that at lower metallicity, so this is an FE on H of minus 2.3, you have a much higher frequency of closed binaries, whereas at high metallicities, you have a lower fraction of closed binaries. And the way to translate between these two curves is that the integration of this curve up to 10 to the 4 days is the closed binary fraction in total. What that means when you actually propagate that through into our binary population synthesis codes is that a metallicity dependent binary fraction, which is shown in the curves here in this figure, the colored curves, leads to a much wider on average initial distribution when compared to initially log uniform orbital periods at zero age main sequence. The reason that this is quite important and interesting is because most studies have assumed this log uniform orbital period distribution. And so indeed, there's quite a difference here. And importantly, this effect of a more wide orbital period distribution at zero age main sequence on average is mostly affecting the solar metallicity zero age main sequence population. Why do we care about that? Well, we think that the majority of star formation, indeed, if you believe M12I is like the true Milky Way, which is maybe not such a great assumption to make, but broadly speaking, we think a lot of the star formation in our galaxy has primarily formed at or near solar metallicity. So if you consider the effects of this initial orbital period distribution being on average wider than what we've previously assumed, and you combine that with this competing effect that the majority of star formation is at solar metallicities, that could significantly affect our double white dwarf population that we think Lisa will observe. So we've combined both of these effects with our binary population synthesis code, COSMIC, which is a code that I developed during my thesis. And yeah, I won't go too much into detail on COSMIC. If you have questions about it, do ask. I'm happy to talk to anyone and everyone about it, but we do have documentation for you to check out as well if you don't want to talk to me directly, which maybe the docs will be more fun. So we use COSMIC to simulate the double white dwarf population to convolve in different binary evolution models with these initial orbital period assumptions and star formation history assumptions. And our models that we picked start out with a fiducial model, which the formation scenario broadly for our double white dwarfs that are going to make it into the Lisa band are you start out on the zero age main sequence. The first more massive star evolves off of its main sequence, goes into a common envelope, leaves behind a strip star and a main sequence star. That main sequence star evolves off of its main sequence, goes into a common envelope itself, and leaves behind a close double white dwarf. In our fiducial model, we assume the standard alpha common envelope prescription that many people do in these types of studies. And we assume that alpha is 1 here. So that means that the orbital energy going into this common envelope is exactly converted into some magical energy that is going to unbind this envelope at an efficiency of 1. We consider a much less efficient common envelope prescription. So it's the same type of idea here. Again, you have zero age main sequence stars, a common envelope, a strip star plus a white dwarf, and then a common envelope again. But the difference in this alpha 2,5 model is that alpha is 0.25. So instead of being perfectly converting orbital energy into unbinding your envelope, you have to put in 4 times the amount of orbital energy to unbind that envelope at the same rate as our fiducial model. What that effectively leads to is many, many pre-double white dwarf formation stellar mergers. So alpha 2,5 is going to produce significantly fewer double white dwarf binaries compared to our fiducial model. On the other end, we do a very efficient unbinding model, where here we set alpha to 5. And same idea, except alpha of 5 is actually going to allow many, many more double white dwarfs to survive because there are very few mergers that happen inside of the common envelope. As a completely different way to study this, we also considered a model where instead of assuming that this primary star goes into a common envelope first, we assume that that mass transfer remains stable. This ends up producing a little bit wider of a system here, and then going into a common envelope and again producing a bit wider double white dwarfs and also leading to much fewer mergers. For the gamma alpha aficionados, our Q3 model is kind of like basically the same thing as a gamma alpha here, because this stable mass transfer leads to less shrinkage than a standard alpha common envelope would lead to. So we combine all of these models with our initial orbital period distribution that is metallicity dependent and assign ages and metallicities based on the latte suite. And then because of that, or looking at that interplay, we can actually count. I don't think that you need to look very much in detail. You can definitely check this out in the paper. But the point is that the interplay between our binary evolution models, which are the different rows that I'm showing here. So this is our fiducial, alpha 2,5, alpha 5, and Q3. That interplays very strongly with the initial metallicity dependent 0H main sequence conditions, and therefore changes quite significantly the number of double white dwarfs formed per unit solar mass as a function of metallicity. And specifically, you can see some pretty significant differences, for example, between our fiducial model for helium plus helium white dwarfs, where we really carve out a significant portion of our helium plus helium progenitors because they merge during common envelopes. You can indeed dig through all of our data and understand all of the reasons for all of these different trends, but of course I don't have time for that. Instead, we can jump straight to what the LISA population looks like. So we can count up all of the sources that have gravitational wave frequencies that exist in the LISA band as a function of their metallicity by assigning the ages and positions and metallicities based on galaxy M12I, as I discussed. And what we can see here is that in our model, sorry, I haven't told you, it's the end of the day, what F50 is. F50 is just comparing what a standard model would be. So assuming a 50% flat binary fraction with a flat uniform distribution. And so importantly here, what I want to point out is that because LISA is sensitive to mostly very initially short orbital periods, what we end up seeing is that in almost all cases, our original models predict many more double white dwarfs than our updated models with this metallicity dependent binary fraction. One thing that I want to highlight is that the models where we have a fair amount of stellar mergers or double white dwarf progenitor mergers, we don't see as big of a difference between the metallicity dependent binary fraction and the log uniform assumptions. And that's just because there are so many mergers that it washes out any of the differences here. Once we have our cataloged sources, we can, of course, I'm going to calculate their LISA sensitivity. Tom and I have been all over the place advertising legwork because we really, really, really want to help people do these calculations simply and easily. We've banged our head on it enough times that we want nobody to ever bang their head on it again. So we can use legwork to count up the power spectral density in LISA for all of our different models. And the thing that really stands out here is that the effects of a metallicity-dependent binary fraction are much more obvious in populations like Q3 and alpha-5, which are not dominated by the mergers of double white dwarf progenitors. Indeed, in those particular populations, we see a reduction in the height of the double white dwarf foreground that's quite significant. In our other models, which are more dominated by mergers of double white dwarf progenitors, we don't see too much of a difference. We can kind of like highlight these differences quite a bit more by just looking at confusion fits here for our different models. And what I'm showing here in the bottom is the ratio between the number of sources in LISA based on our metallicity dependent binary fraction and a flat 50% binary fraction, flat uniform distribution. And you can see in our different models, this is alpha 2.5, our fiducial, and our Q3 and alpha-5 models. As you increase the number of sources, you're going to see a larger reduction due to this initial orbital period distribution implied by the metallicity dependent binary fraction. One thing that I really want to highlight finally is just that, and Tom Wag talked about this a little bit in the first session, one thing that I want people to take away very seriously is that the number of LISA double white dwarfs that we predict from our models varies by more than 2 orders of magnitude with different Roche overflow assumptions. And so since we don't know exactly what the true case is for these Roche overflow interactions, we don't know if alpha 2.5 or the fiducial model or alpha of 5 or Q3. We don't know which one is correct, and these are going to predict very, very different results. So if you are running binary population synthesis simulations, I really highly encourage you to run lots of models, really explore that parameter space, because if we know what our uncertainties are, we can use LISA to help us in the future. And with that, I'll just finish on a few punchlines. So first, we know that zero-age main sequence binaries have metallicity-dependent features, and we have shown in our study that it could really seriously impact the formation of double white dwarfs that are observable by LISA. We find that the double white dwarf foreground is reduced for binary evolution models, which produce large double white dwarf populations. We also find that the double white dwarf foreground ends up being rather unchanged for binary evolution models, which produce smaller populations. And finally, I will highlight that we are putting all of our data, all of the results, all of the code used to produce our paper in a GitHub repository using Show Your Work. I'm happy to talk to folks about that if you're interested in it. But at present, I'm not advertising our GitHub because our Show Your Work install right now is totally busted. So check back later for when that's not totally broke. And yeah, that's all I have.
Thank you, Katis. And there is time for question. The first came from the Gleasis element. Please, thank you.
I was actually close, but I do have a question. So, does my sound work now?
Yeah, I can hear you.
Oh, great. Hi, that was very nice. Thank you. One question is, have you looked in any way how these different models compare to the observed sample of double white dwarfs? Because of course, you know, in a way, we're sort of reverse engineering partly, because some of the work we've done in the past is quite heavily based on these observations. So I think that would be.
Yeah, I totally agree. So we have not taken we've not taken our results and placed them in context of EM results yet, but that is something that's basically right next on our to-do list, because we have all of the data. We just need to, instead of use legwork to determine the gravitational wave signatures, we need to see what how they will show up in surveys like Gaia and yeah, the ELM survey specifically. So that's on our docket to do now that we have all these data sets.
Okay, thank you, Grace. And the next question came from Tyson. Please unmute yourself.
Yeah, when you say the double white dwarf foreground, is this after you have stripped off what you think will be resolved? Or is this the entire population in the leaf?
It's, well, okay, so it's both. Let's say that. The way that we hack the foreground, Tyson, you'd probably become nauseous again based on this, but we hack our foreground by doing a running median through the PSD. So that's how we get our foreground here. We tested to see whether that's a terrible hack by doing calculate this SNR, remove them from the PSD, calculate the SNR again, remove everything that's SNR of 7. And like when we do that, we get something that's very, very similar to just running a median. But that's our height of the foreground is what we mean that's what we mean when we're saying foreground.
Yeah, thank you.
It's super interesting.
I could not hear. So
yeah, I think I missed.
Sorry.
Go ahead, Tyson.
So I was just saying that the number of resolvable binaries is also particularly interesting, and depending on how densely packed they are per frequency bin, just because the confusion noise level goes up or down does not necessarily, okay, here.
Yes, we agree. So we, the way that we actually, no, now, well, okay, so we calculated, what we do is we calculate the, we calculate our running median and add that to our SNR. And then for all of our resolved systems, it's the ones that sit above that running median. I feel like we have a terrible delay, Tyson, and it's really stressing me out. I hope that I'm not talking over you.
I think Tyson was rather quick to mute himself and cut himself off, but I don't think there's any miscommunication. Yeah, a follow-up offline would be ideal.
Okay, and the next question came, Alessandra, please unmute and ask question.
Great talk, Katie. So as somebody who's interested in going the other way and taking the foreground signal and trying to learn about the galaxy, right, how unique do you think that this shift is, right? Is it going to end up being super degenerate with just the mass of the Milky Way? Or do you think that if I had a spectrum, I could actually try to go and figure out what the metallicity of the population is?
Yeah, that's a fun question. I think in order to back out the star formation history and like specifically like metallicity distribution, all of that, it really depends on whether or not we figure out what the right binary evolution model is. Because if I think that once we figure out that, then it's much easier to then say, okay, if we understand the binary evolution, you can absolutely model the hell out of the star formation history. So I think that that's possible, and I'm fairly optimistic about it because, let's see, one of the things that I've been thinking a lot about here but didn't talk about at all is that we don't just have to think about this end state. We can think about lots and lots of states. So part of this study is kind of driven by the fact that we actually have nailed the zero age main sequence population down quite well. There is an increasing number of white dwarf plus main sequence binaries, and there's going to be an even bigger number of these things when people pull out a really lovely data set that they could probably get in Gaia. So we're about to have, in the next few years, fantastic data sets to compare intermediate phases to, and I think that that's going to be like totally revolutionary in terms of being able to determine whether this model or this model or this model or this model or somebody else's model is much more reasonable than the others. So I'm optimistic that on like 10-year timescales, we can probably get a handle on these models. much better than the cartoons that I'm drawing on the screen right now.
All right, that's really exciting. Thank you.
Yeah.
Katis, I have a question. So you have a 4 model here. So what is the difference between the first 3 one and the last one?
Yeah, so the biggest difference between these models basically are producing double white dwarfs mostly through 2 common envelope phases. So there's always going to be a common envelope from the primary and a common envelope from the secondary. This model assumption changes the physics that determines whether you go into a stable Roche overflow instead rather than a common envelope here. And so we find that the majority of our double white dwarfs form through a stable mass transfer and then a common envelope.
Okay, so what is the main physics you put in the model Q3?
The difference, yeah, so the main physics is just whether or not that there is this stable mass transfer versus the common envelope.
Oh,
oh, go ahead.
Oh, no, go ahead.
Yeah, so the stable mass transfer tends to result in overall wider post mass transfer systems than a post common envelope system.
Okay, thank you. And I'm interested in the compact course. The course that you mentioned.
Yeah, in Cosmic, yeah.
Cosmic, yeah, Cosmic. So what is you because I saw you say something related with yeah, like is that the open course? And
yeah, so this is Cosmic is totally fully developed on GitHub. You can see all of our late night upset commits that the codes are broken and whatever. We do everything totally openly. Everyone can see everything. Yeah, it's all, you can check out our GitHub. If you search Cosmic PopSynth, we didn't think about the fact that if you name a code Cosmic in the field of astronomy, that it will become impossible to Google immediately when we first named it. So Google Cosmic PopSynth and it will come up.
Okay. Yeah, thank you. So if you have any question, can I follow up with you?
Yeah, definitely. Yeah.
Thank you. So I don't see any question in the chat, and also I don't see any hands up here. Okay, so let's thank to the Katis, and yeah, it's very interesting talk about the metallicities and gyro, and so we did they have a hands up here? Okay, no. Yeah, let's thank Kati, and one more time we would like to thank all the speakers today. And today we have a 6th speaker talk about the detectable for binary black hole, binary neutron star, binary black hole neutron star, and also is interesting about the stellar origin black hole binaries with LISA. And we also learn about the observational from the galactic binaries, Magellan clouds with the new perspective from the LISA, and also metallicity abundant to study double gyro formation. So we go from the observation talk and simulation talk, and so it's very interesting for our section today. Yeah, so if you have any question for the own speaker, I think most speakers in here, please go ahead. And if not, yeah, we think that we can follow up with the speaker, if kind of offline discussion. And yeah, Alada, Taylor, do you have anything that you want to have?
No,
Yeah.
No, Lan, that's I think everything's been covered. I mean, if people want an easy way to follow up with their speakers, they can use the chat on the conference, and they can also use the conference to find other people. But no, thank you for chairing, and thank you all the speakers again.
Okay, and thank you, and yeah, you have a good day. Have a nice day.